Again, all these videos here in section 2.7, formal limit definition, are set up for you. The first two have specific values of epsilon. One of them is the one that you did on the back of the sheet that I handed out last time. But then we have three formal limit definition proofs, along with the steps we need to cover to do them. And really just keeping it fairly straightforward and simple. We follow the exact same pattern we did with the numerical examples, where we had 0.01 for epsilon. And now we just use epsilon there and figure out what delta needs to be in terms of epsilon. Let's see, the first example, let me just pull it up and see what it will give us here. Hopefully it's set up to play. Yep, it's coming up here. A couple things that you might do as you're playing it. I tend to not like to see all the ink ahead of time when I'm trying to watch a video like this. So you might want to click on this little cubic-looking graph. It has the grayed out part on the right. So if you click on that, it will hide things that haven't been shown yet, actually once you're playing it, I guess. I'd also probably recommend increasing the size on this. Let's see. You can always scroll down here to see it as you're going. But again, I would click on this. I don't know why it's not doing that yet. Maybe once you start playing it, it will allow you to do that. You've used one of these before, right? First chapter. So again, it doesn't look like this one's maybe got Adobe Acrobat 10 on it. That's my only guess. That's why it's not playing or letting me change this. But it's got the player on it, which is interesting. I'm not sure why it's not working. But anyway, what you do when you click on this, it'll make that grayed out part disappear, and everything will disappear, and you'll just see the green appear as I speak, as I go through it. And it talks about it. So again, let's see. This is a different one than what you did in the back, but it has another specific value of epsilon example. So here it was 0.01 was our choice for epsilon. And we go through and we figure out what delta needs to be. So in this case, as you'll see, delta ends up being the minimum of two values. We take the absolute value of each of them, so it's the closest to 0, if you will. In this case, it turns out to be 0.002, actually. That's the one we choose. Sometimes it's the one on the left, sometimes it's the one on the right. But you choose the minimum value, and then you can give your guarantee for these numerical examples. Okay, so you can guarantee that if x is in the interval within 0.002 of the target value of 2, that's what the target value was, and x is not equal to 2, then x squared minus 3 has to be in the interval from 0.99 to 1.01. In other words, within 0.01 units of the limit value of 1, which again we shouldn't be too unsure about what the limit should be. Here it's continuous, so we can plug the number in. We know what the limit should be. But this proof is done to show that it satisfies the idea of closeness. And of course, we're dealing with simple examples because they're easy to work with for the proof. But this kind of limit can be done for discontinuous functions as well. Not that they're always easy to write out. Okay. In fact, as you'll see in my third example of the formal limit proof, occasionally you can do the first part, which is to find delta, but you can't go back and do the second part, which you'll see as you go through these videos, which is to go back the other way. And the reason for that is that we end up with some expression for delta that isn't easy to work with. So, oops, I didn't mean to go back there. Let me go back here and go back to Chapter 2 lesson videos. And let's see, this is the last one here, the third formal limit proof. See if it does any better, I don't know here, at playing. But in this one, you've got, maybe make this a little bit bigger again. You're asked to take really the one we looked at before. This is the one you're doing the work on in the back of the sheet, except we're going to take it, make it more general. So instead of making that difference between the square root of x and limit value, so f of x and minus L here, making it less than 0.01, we're making it less than epsilon. It's going to go through the exact same process we did with 0.01, this time with epsilon. And then as we go down here, we'll find that at the bottom of it, just like you did with the 0.01, you have to take the minimum of two values. But this time, that's not just a number. It's not easy to tell which is the smallest. And even if you pick one of them, as I think this one ends up being, I think, the smallest generally if you sort of look into it, you only end up with, when you go back through it, negative epsilon on the left and some other expression on the right. It's hard to tell whether it's exactly within the range we need it to be. And it can be proven if you do enough extra work that it does. And if you want to show me that work, to try to show going back the other way as you'll look at the other two previous examples that are here, you can get some bonus points if you can actually take one of these and show that it's less than this one is, and then go through and show that you get the right end point being less than epsilon, because that's, again, what you need to prove going the other way. But you have to sometimes stop here after finding a delta. But that's usually, again, in the books, as you look at a couple different calculus books, you'll see a lot of times with the more complicated functions, that's what they have to do. They find a delta that makes that happen, and then leave it there, and you know it's going to work. You just haven't gone through the formal proof yet. Now, let me show you one of the formal proofs. You're going to be able to listen to me talk about it more next time, but just to show you what this looks like, or not next time. You're going to be able to listen to me talk about it in the video as you listen to it. But just to point out some things here. After it loads. Get a little bit bigger again. Okay, so here we have a complete formal epsilon delta limit proof, and in this case, it's the same one as I'll show in a previous example with a 0.01, I think. So there's actually an example, another numerical example there with a 0.01, where I go through this, and then I'm going through it now with the epsilon. Turns out, and you can pretty quickly make the f minus L, absolute value of f minus L less than epsilon, transform it to a point where you get the absolute value of x minus 2, which is what we're looking for with the target value here, to be less than something in terms of epsilon. In this case, it turns out to be epsilon over 3. And that's your choice then for delta. We then go through step 2, which is to prove that this is less than epsilon given any epsilon greater than 0 for, actually 0 is strictly less than absolute value of x minus 2 less than delta. This I talk about in the video, but what does it accomplish to say 0 is less than this? Because it has to be a positive number anyway, right, or a non-negative number, although it could be 0. Why are we saying it can't be equal to 0? What's that equivalent to saying? That's right. Okay, we've said that explicitly in some of the previous examples. Explicitly means we spelled it out. Okay, but here we just made it more concise by putting that inequality in to show that x can't be equal to 2, the target value itself. So here's the actual proof. Suppose epsilon is greater than 0. Assume that our absolute value of x minus 2 is greater than 0 and less than delta equal to epsilon over 3. In other words, x is not equal to 2, and x is within epsilon over 3 units of 2. That's what we're saying here. If that's true, can we show that the expression absolute value of f of x minus L is less than epsilon? And that's what we're hoping to show. We sort of know we're going to be able to do it here, but we do a little work just like we did up above. Get it written in terms of absolute value of x minus 2. Replace that with what it's less than. Put a less than sign to show the inequality here. And then 3 times epsilon over 3 is epsilon. We've shown that the original absolute value of f of x minus L is less than epsilon, given this choice of delta. So it basically makes it very clear, showing that it does indeed give us what we're looking for. It's a proof. It is something I want you to be able to do, and it now allows you to do the rest of the problems in 2.7 once you watch these videos. Okay, I think there might be 1 or 2 at the very end that are infinite limits. I'll look at that, maybe send you an email about a couple that maybe aren't covered yet. But it does allow you to do some of the additional limit proof ones that I'd like you to be able to do here. If you have questions on it, we can go through more of it next time. But what I want to do today is get ourselves into the definition of the derivative. So I've covered a lot of this material in here. And if I see that I didn't cover the second example on your sheet, I'll be sure to either do a video or cover it in class next time. Okay, the numerical example there, that is on there. So it's very similar to what I did in the previous one I just showed you here. Now, before we go all the way back to new notes here, I want to show you, whoops, this one actually. There's something else that's up now that I want to get you started with, and that is discussion questions. Okay, I've got a series of discussion questions for the semester we're going to be working on. And at this point, we're ready for the first discussion question. And I believe the second one, too, at least will be soon. So the first discussion question is one that needs to be completed by Wednesday of this week. And it's pretty quick and easy. It's a 5-point assignment. Just requires you to put in several sentences to describe or explain the answer to this question. So it says, in your own words, explain what we mean when we say that a limit has the form 0 over 0. Why is it that a limit of the form 0 over 0 is indeterminate, unlike a limit taking the form 8 over 2, which would give us a limit of 4? Do your best to explain to me in your own words. So you're not necessarily looking this up anywhere, right? You're just trying to explain it based on what we've been talking about, what we've learned. Your response does not have to be lengthy, although it should be at least 3 sentences, okay, and should be clear. Okay, so this is informal writing, one of the components, so it's not being graded necessarily on spelling and grammar, but I will want to be able to understand it, okay, and be able to read it clearly. And it should have clear understanding or show clear understanding of the concepts. 5 points. 5 points if you cover it well, you answer the question and you answer it clearly. A little bit less if you aren't quite as clear or not able to answer the question, of course, at all, then it'd be 0 if you don't really answer the question or address the question at all. Okay? There's another one on here. Let's see. It's actually this one. Let's see when we're going to be ready for that one. That one, actually, we need to do what we're going to do today, so we'll see after that. I'll tell you more about this one. So for now, wait on this one. Do number 1. You should be good with that one to work on it. Other than that, I think we're good. An angel. So let's get ourselves back now to our notes and get ourselves started here. Okay, as I mentioned to somebody, you may have all heard me, but I didn't get a chance yet to do the rough drafts of your essay. I'm planning to get them back ASAP. I'm hoping here by Thursday. I've just been backed up with videos and, well, like I said, my computer crashed this week. So it actually finally wouldn't let me get back into it yesterday during the day at all. And so I'm thankfully I backed up most things. But anyway, I had to sort of set up a whole new computer. At least there was one available. 6. And as you've seen, I guess I've been busy creating videos of the limit definition too. That was what I really have been doing a lot of work over the weekend. 7. All right, so let's get started. A derivative. Some of you have had calculus somewhere before. How many did take calculus somewhere before? A whole bunch of people have. Okay, so don't give it away, as we go through this process. But, you think about it, make sure things are clear. Hopefully things will even fill in some gaps you may have had. So a derivative is a function that represents an instantaneous, anybody know? Rate of change. Good. In one variable. This is the dependent variable. Often we use y, okay, but it can often be other things as well. But it's the dependent variable, like y is normally the dependent variable in a function statement. Y equals f of x, right? Okay, so with respect to or in response to a change in a second variable, this is the independent variable, often x, or, as we'll see, in many applications, that second independent variable ends up being real-life applications. What do you think changes? Causes other things to change. As it changes, lots of stuff changes. Time, that's right. So most applications, although there are a lot of other exceptions to this, but there are a lot of applications where time is the independent variable. As time changes, almost everything changes, right? I guess I gave it away if you looked at the next sentence. All right, so almost everything changes as time passes. Okay, let's list some examples of some things. Let me grab my notes here. So I have a few examples in here I want to be sure to mention. Sorry for the delay here. You can think about some answers here. There we go. All right, so what's one thing that changes as time passes or might change as time passes? Distance, which I suppose what you mean by that is position of an object. Okay, which means it's going to have some displacement. It will travel some distance, okay, but that's what we would mean by that. Rate of change in position would be your velocity, another name for that, right? So rate of change in position Rate of change in position is sometimes called, or is called, velocity. All right, what else changes as time passes? Sorry, what? Okay, so yeah, how would you say that? It relates to population, like if it were bacteria cells. So we might put that down. I'm trying to think the right word for that, but I know what you mean. That's true. So mass, maybe, of something, or volume of it, or there's a number of ways of saying that, but I'm not sure what the term would be. But it's a good example. I'm not sure what to write there. How about height of a child? I think of that because I got 2 kids, so it's changing all the time. The rate is slow enough you don't notice it by just watching them, but if you don't see them for a few weeks, months, sometimes, come back and you really notice that there's been a definite change, and there's a rate of change that's involved there. Let's see. This is similar to what you were talking about, an amount. So the amount of a certain substance in a chemical reaction that's a C there. Here's one that didn't happen too much this summer, but does all the time, at least to some degree. The length of grass, of the grass, in our yard. And I guess I don't have a lot of space here. Another one would be the return on an investment. Okay, the amount of money that you make on an investment, or the value of an investment might be even a better way to say it. Right? So the value of an investment. Okay, and there's many, many, many more things that change as time passes. And of course, there's other things that change as something else changes. They're not always having to do with time. Okay, this is just one of the main examples that we'll see many times in this class. Okay, so let's go ahead and look down below here. The derivative of calculus can be applied to any of these situations to give us the rate at which each of these quantities is changing at any given point in time. It's an instantaneous rate of change. How fast is it changing right now? How fast is it changing right now? And so on. Sometimes that's hard to figure in a real-life application. You've got to take data and approximate that. We'll talk about how to approximate instantaneous rates of change using, anybody know what you use to approximate an instantaneous rate of change? We did it the first day of class. An average rate of change. That's right. Remember doing that? Average rate of change. That marble we dropped from the cliff, right? So that's exactly what we're talking about here. Now, a graphical concept that's linked closely to the idea of a derivative is the idea of a slope of a line. And of course, slope has to do with rate of change in that if you have a graph of a function, what is happening on this portion right here to the function values? They're increasing, right? So is your rate of change positive or negative? It's positive, right? So here we have a positive rate of change. And what's the slope there? Positive slope, right? Okay. What about over here? Negative rate of change? Negative slope for sure, right? Negative rate of change, it's decreasing in value. Negative slope. And how do you determine the slope of a curve, by the way? Do we usually talk about the slope of a curve? At least in past experience before calculus? No, right? In order to determine the slope of a curve, what do we need? A tangent line. Yeah, we need it to be able to look at a line there. Otherwise, if we don't have a line that's associated, we're going to have a hard time getting a slope number that's meaningful. All right, so what we should see happen, and this is what you can do with your straight edge, is you try to see the same amount of the curve on both sides that you're going to sort of go through, if you will, sort of a symmetric thing, in order to know you got a tangent line. So this worked all right. I'm not going to draw the other one because it took me a little while to put it in there, but you get the idea. If I drew it in, I could actually draw it in, I guess, by hand, but you guys are going to, this is not aligned very well. That's the problem with that one. But you can sort of see at least the idea of what we're trying to do. Anyway, you got the idea, though. It's negative slope. And what happens at this point right up here at the very peak? Yeah, we get a zero slope. And what does that mean about the rate of change? Zero rate of change. And in fact, thinking about the fact that I've just said that the derivative is a rate of change, that means the derivative of this function whose graph we are seeing here, is zero right here. It's got a horizontal tangent line right there. I'm not going to be able to draw this very well probably, but anyway, so you've got a horizontal tangent line there, zero slope. Now, slope of a line is, of course, calculated with a formula. M equals, well, let me do it this way first. Change in y over change in x. We often write y2 minus y1 over x2 minus x1, this idea, to represent the slope of a line. We have to know that it's change in y over change in x, or change in the vertical over change in the horizontal variable. Sometimes those variable names will change as we look at different graphs, different functions and applications. And now what I'd like to do is have you try just a quick exercise, and while you do that, I will fix the alignment on here. But this exercise has to do with slopes of lines. It should be really straightforward, but good review to make sure you remember all these slopes and how to calculate them just by using rise over run from the graph. All right, so take a moment to do these once you get it, and then we'll look at them together up there. By the way, our test, first test is scheduled, I think, for this Friday. I'm planning to move it to Tuesday, just so we have a little bit more time to wrap some of this material up. Yeah, I'll be giving a review test to help you out, too, as we go here. But take a moment to try these, thinking about what we talked about up here, and then we'll look at them together in a minute here. Okay, looks like some of you are finished. Many of you are finished. All right, let's see what you've got here. So line number 1, this horizontal line, what is the slope? 0, okay. Line number 2, here it is, right here. What's the slope of that line? 1/2, so we go up 1 and right 2. You can see that right here. Keeps going, so 1/2. All right, so line number 3. Looks like a slope of 1. 1, 1, it looks like it goes through right here. 2, 2, and so forth. So slope of 1. Line number 4. Like up 2 over 1, up 2 over 1, so 2. Line 5, vertical line. Undefined. Okay, and we can have an undefined value of a derivative if it's got a vertical tangent line. This is what's going along with this, okay? 6. Looks like up 4 and over 1, so 4. And 7. -2, right? Down 2, right 1, and so forth. So -2. So this gives us an idea, at least, of the slopes. Hopefully these are pretty easy. If not, review your slope idea. Remember, slope is rise over run. That's another thing we could have said here to define it. Okay, back here. Oops. So m, or slope, equals rise over run. Of course, you guys know that already. All right, down here at the bottom, let's summarize some stuff. Lines with positive slope slant upward or up as you move to the right along them. Okay, so positive slope, you're going upwards. And of course, lines with negative slope slant down or downward as you move right along them. Okay, so that's important. Positive value of a derivative, negative value of a derivative. Increasing, decreasing corresponds to it. All right, let's see here. Next thing on here, tangent lines. We talked a little bit about tangent lines already. In order to determine slope of a curve, we need to know the slope of its tangent line. And when you think of a tangent line from past courses before calculus, what geometric figure do you usually associate with it? Someone said it. A circle, usually, right? What's a tangent line to a circle? What's it defined to be? Touches the edge of the circle only once. That's right. If I can say that right, yeah. So here's an example, right, of a drawing of a circle with a tangent line, right? Okay, drawn nicely, professionally on here, right? So I didn't have to try to do this one by hand. So you also notice it's perpendicular to the radius here of the circle. It's sort of interesting. There's something similar to that when we get to regular curves. There's a normal line to the curve, and the normal line would be sort of like this, perpendicular to the tangent line. But anyway, we're not there yet. All right, so back to our notes here. Let's consider the graph of y equals x squared plus 2. We have that over to the right here. Suppose that this were the path of a highway, and you're driving along this highway from left to right. Okay, you've got your car on here. I didn't get technical enough to have the car drawn on here, okay? But you're driving and your headlights are on, so it's nighttime, and this makes it a little easier to visualize what's going on here. But as you drive along this road, okay, you're moving this way, your headlights are pointing this way, right? So your headlights are like the tangent line to the road, if you will, as you keep going. So let's see, if we consider usual compass directions, so let's see, I guess that would mean this would be north, right? Due north. Then as you move down to the vertex at 0, 2, which direction would the headlights be pointing? So you keep moving down this line here. What happens here? They're horizontal. They're pointing which direction? Due east here, okay? So that would be your compass direction. So you'd say due east or east. Okay, what slope would be associated with this tangent line? Slope of 0. Talked about that already a little bit. So your derivative at this point should be 0 at 0, 2. Okay, or x when x is 0. And of course here our derivative value should be negative. It's exactly identical to the slope of the tangent line at the point, the value of the derivative. Okay, and over here, if we picked a point, the slope would be positive because the function's increasing. It's got a positive slope here. Slightly better with the alignment I did here. All right, so let's see. The derivative of a function tells us the blank of the tangent lines to this function at every point. What's the word here? The slope of the tangent lines to this function at every point. Okay, this slope corresponds to the instantaneous rate of change in the function f with respect to x. Okay, assuming this is our function named f here. All right, so we're ready now for the next page. Actually here. So now what we want to do is actually define the slope of a tangent line at every point on an arbitrary curve. So this has just been chosen arbitrarily as a function that makes the picture easy to do or easy to work with. And we want to figure out how to write this function so that we actually get the slope of the tangent line at a value of x. Now, let me draw a few things on here that will help us. I guess we can use red for this. This is our x value. Okay, and x can be moved around. Okay, I suppose we could make it x sub 1 if we wanted to. It's a specific x coordinate we're going to work with for the particular point P. Okay, the coordinates of this point P would be what here? X comma f of x. Okay. All right, so that's the coordinates of the point P. Now, here's the dilemma. In order to determine the slope of a line, we need more information than a single point. Right? How many points do we need? We need 2. Okay. Do we have another point on the line somehow? Can we easily get another point on the line without knowing the slope or the derivative formula here? No. Okay, so that's sort of our goal. We've got to come up with a way to determine the derivative without knowing how to find the derivative already. So what can we do to get close to that slope and maybe begin to approximate the slope of this tangent line? And it depends on if you read section 2.1 or not, because they did talk about this there. But so what can we do? You need 2 points, right, to determine a slope. Could we find another point on the curve maybe? And maybe do something with that? Let's see. So I'm going to do one way out here. Just make it easy to see what's happening at first. So we'll make this point Q. And let's see. That point is going to be a new x coordinate Let's put the distance in between these to be change in x, delta x here. And so the x-coordinate of this point will be what with respect to that x? X plus change in x. Good. Okay. Now, if this x-coordinate is x plus change in x, what's the full coordinate pair for q? F of, what's inside? Okay, x plus delta x is in there too. Good. Okay, so we've got the full coordinate pair for both points. Now what we want to do is actually consider what we'd have here, a line drawn through these 2 points. And maybe I could actually do this with my line helper here. Let's see. I guess I'll just use that one. So I'm going to go from down here. See if I can get to go through that point too. And maybe I'll change the color on it. Make it blue. Oh, I didn't make what I wanted blue here. Undo that. All right, let me pick this again. There we go. Now it'll work. Make that blue. Light blue. Okay, and go back to here. All right, so we've got one example, and in this case, what we come up with for a slope is positive, but it's not very close to that slope yet. But how would we determine the slope of that line using the points we've got? So the slope of the, what do you call a line that cuts through a curve at 2 points? Secant line, that's right. Just like it would be for a circle. This comes from that language. So the slope of a secant line here would be equal to change in y over change in x. What's the change in y here? Y coordinates? Good. Okay, and the change in x coordinates? Yeah, it would be delta x because it's x plus delta x minus x, which simplifies to, top's the same, delta x, which makes sense, right? Change in y over change in x. Okay, so this ends up being an expression for the slope of the secant line that we can think about. But you can see right now we didn't do a very good job of approximating. So how can we improve this approximation? Yeah, move q closer to p. So we're going to put a point a little closer here, maybe put it right here. Okay, this would be a q sub 2. We'll make this q sub 1. Okay, and there we can put our point through our line through, excuse me. And let's see if I can just do this one by hand. Get the idea. Okay, and we see that it definitely is closer in slope value to the tangent line. We could then try it again, going closer yet, put a point right there, and now it's getting quite close to the slope of that tangent line. Now what happens when change in x becomes 0? What happens when it's exactly equal to 0? Can we calculate it? What do you get here when you put 0 in for change in x? You get 0 on the bottom. What do you get on top? 0 on top. You get 0 over 0. What was that? Indeterminate, right? Of course, it's not a limit yet, but it's an indeterminate result even here. Okay, there's a problem with it. But what we're interested in doing now is to consider how can we then come up with the exact value of the derivative or the exact value of the slope of the tangent line using this expression, using this thinking we just used, right, to cause that point to get closer and closer to p. What's changing as we move the point q closer and closer to p? Change in x is changing, okay, as we move the point q closer and closer to p. And what's it becoming? What's it going to? Going towards 0. So let's see if we can't figure this out here. The slope, whoops, Soul. Okay, let's try that again. The slope of the tangent line, which is equal to what we're going to call f prime of x, the derivative of the function at x, is equal to, what are we going to do here? Making change x go to 0. What's that called? A limit, okay, guys, somebody was saying something. A limit as what changes? Delta x goes to 0 of this thing, right? This expression, f of x plus delta x minus f of x over delta x. We're taking a limit of the secant line slope as delta x goes to 0 to come up with the exact value of the tangent line slope, which is our derivative value at x. Now, we've done this for an arbitrary x coordinate, which means what we end up with is a function of x that has an x in it all over the place, every place we have here. We could put an actual value in here and do the actual limit with a value in there, and occasionally we'll need to do that because we won't have an exact formula yet. But in terms of doing a limit, which is the variable here? X or delta x? Delta x is the variable that's changing, right? X is considered constant. It gets treated like a number in the limit process. So we actually already know how to do these limits, but it turns out this is just a limit of the form we've been working with in Chapter 2 all along. This is Section 3.1 now, but we're using that same limit process, and the form of the limit is 0 over 0. If you put that 0 in, so it ends up being indeterminate every time. But we usually will get a value for this. We'll usually get a function of x for this. So let's go ahead now, using this definition of the derivative, and do something with it. Before I actually do that, there's one other notation that we'll see here for the derivative, and maybe I'll put it out front here. It's dy dx. You've seen it in your study of Leibniz, I believe, right? His work and notation. Dy dx represents or is similar to delta y over delta x. So it really has a helpful notation for that. It helps us see it as a slope. Okay, but the dy and the dx are both very small values going toward what I call infinitesimal size. And that's the idea of Leibniz that put this together. All right, let's go ahead now and go down to the next page. Are there any questions before I move on? Seem reasonable? Okay. So let's see what my next thing is. I actually need to do something first here. Let's see. So I'm going to put this back up here and insert a page. This is, now I guess on your own notes, your own sheet of paper. Note, by the way, on that note sheet, I did put your homework from Section 3.1. It's no longer on the other homework sheet, so you're going to have to use this sheet for today. I'm going to put one together. Now, to make our life a little easier, we're going to choose to make h equal to delta x. This will allow us to write our limit definition of the derivative without two symbols each time we use the variable. We're just going to use an h there for our change in x, remembering that that's what it represents. And up here, it's going to be f of x plus h minus f of x over h. Okay, I don't know if you've seen this done before, but it's a frequently used technique to make the whole process a little bit easier to work with, a little bit less notation to plow through as you're doing the limits here, and I think you'll find it easier. But you do have to remember that this is equal to change in x, and you will still see that definition using change in x at times. Okay, and that's important to realize. All right, let's go ahead and give this a try with an example. Example 1, let's say we've got f of x equals x squared. Okay, we want to find f prime of x using this limit definition. Okay, some of you might remember a shortcut for this. Don't yell it out yet, but we'll talk about that in a few minutes. Okay, but that shortcut comes from using the limit definition. And we have to actually come up with several examples to begin to generalize the pattern that we see. There is a proof that could be done of it generally, but we're going to focus on some specific examples here. So let's see, f prime of x equals this limit. Let's start with that each time. Really helpful to write this out anyway. Helps us remember the limit definition and hopefully get it correct. Okay, now the hard part is often this first term on top. And so I'm actually going to have you write that out separately. Maybe I'll put it right up here. F of x plus h. What is f of x plus h here when you put x plus h in place of x in our function? Okay, where does the squared go? So parentheses, excellent. Okay, that's what we need to see. That, for some reason, is often the hardest part of doing these problems, the composition, if you will, of functions that you're doing here to create this formula. If it's easy for you, wonderful. Just make note of that is what you have to pay close attention to usually to get this process nailed down. Okay, so now we're ready to replace f of x plus h with what it's equal to. Keep your limit statements. Very important here. So we got x plus h squared minus, what is f of x here? X squared. Okay, replace that there too. H, of course, is the same. Now, if you put 0 in for h, you get 0 on the bottom, and on top you'd have x squared minus x squared, or 0 on top. It's a 0 over 0, indeterminate form limit. You'll always find that for derivatives. It'll always be that way. Okay, what are we going to have to do next? FOIL. Yeah, we're going to do a little bit of algebra here. So equals limit as h goes to 0 of x squared plus, what's the middle term? 2xh plus h squared minus x squared all over h. Okay, what do we notice happens with a subtraction? Okay, the x squareds cancel. It's okay to cross them out if you want to. You cannot cancel the h's yet. I've had people want to do that here. We actually have to rewrite without those terms if you're going to try to factor an h out. But we do hope to eventually cancel the removable discontinuity, the 0 over 0 part, right? So here we're going to rewrite. While we're rewriting, we might choose to factor an h out. We can do that with the other two terms here. So we're going to write h times 2x plus h over h. Okay, now, can you see what we can do? We can cancel the h's. This is actually a factor of 1, right? This is the removable discontinuity step. So we can say this is equal to the limit as h goes to 0 of 2x plus h in parentheses. Notice the equal limit of this, equal limit of this, equals limit of this, equals limit of this, all the way down. That clear chain of equality using your equal signs and your limit statements has to be part of this process. I want to see it this way, okay? Just want to make sure you're clear on that. Okay, now at this point, will we have an undefined result if we put 0 in? No. So here we're allowed to put it in without needing to state a limit anymore. This is where we take the limit statement away. We have 2x plus 0, which is 2x. Now what we'll need to do, since this is such a long process of equal signs, we need to summarize our results. Therefore, f prime of x, our function, our derivative function here is 2x. Now, is this what some of you might have known before was true for x squared? Yeah, okay, and don't give the rule away yet. Okay, we're going to talk about that. I'm going to generalize this with a few more examples to see that. But we do expect that to be there if you already knew your formula. Okay, now shortcuts that we'll eventually get to are helpful, but this is more key to understanding what's going on and how to apply the derivative of calculus in real-life applications. So we want to make sure we do get this idea of the limit of the secant line slope, or the average rate of change, which is honestly what you've got here. This is the average rate of change in the function. The average velocity, if you will, be equivalent to this kind of writing. We're going to do it with actually different letters, different function names. Position, I think we had it right in our first day of class. The change in position over change in time ends up being the average velocity, and you use that, a limit of that, to come up with the instantaneous velocity. We'll eventually put that up on the board. But what I'd like to have you do now is an exercise which practices some of these. This is going to be something you will eventually turn in next time, but you're going to start it now. Okay, it has 2 sides to it, 5 examples, and I want you to start working at determining the derivatives, f prime of x, using the definition that I've stated this time for you. Won't be stated on the test, just so you know. You'll need to know this limit definition. And go through and see what you come up with. I'll come walk around and see how you're doing. You can talk with your neighbor if you want about it, as long as you're focused on the project at hand. First one is the hardest one, I think. Try number 2. want you to pause for just a few minutes. I'm going to show you something on the computer to help get a fuller visualization for what we're coming up with here. So what we're looking for, again, is a function of x, f prime of x, that gives us back slopes of the function at every point, slopes of the tangent line to the curve at every point on the function. And it's really a very powerful function that we get back here. In the example of x cubed that you're calculating the derivative of with the limit there, okay, it will give us the slope of the tangent line at any point along the curve, okay, including down here at 0 and so on. Now, in this case, let me just show you what that would look like as we move along the curve. You can see we're getting different slope values. They're up here. Tangent line slope right here, 8.26 is right now. A little hard to read in the coloring of the projector, but if we come up here, we see the slopes are getting smaller, and in fact at 0 we see the slope is 0, okay, and then it keeps going. And the f prime of x gives us all of these slope values. And in fact, it's a function itself we could graph separately. We'll be looking at that later on as something specific that we want to make a relationship, or get to see the relationship between the graph of a function and the graph of its derivative values, its slopes. Okay, but I just wanted you to see this as what we're coming up with, a function that will give us all these slope values. Not just one point, but everywhere. Now, another thing I can show you up here is the secant line and tangent line idea. Okay, we talked about how as we move that secant line closer to the tangent line, that our secant line slope approaches, the green slope here, approaches the one in the purple box. So we have 1.96 for the one in the purple box, 1.909 for the one in the green box. If you get too close, it says no secant line because, of course, you have just one point. But you can see how, indeed, the values do approach it as we come in from the right or as we come in from the left. Okay, again, if you get too close, it's not going to work. Okay, but this is the idea that we just worked with and looked at on the screen, sort of doing one at a time. All right, now, we're running a little bit low on time. I want to get back to the notes and show you some hints here. Let's see where I want to go with this. All right, first of all, with this one, first one, seems to be the hardest one for people. Let's just talk about this a little bit, what we should expect here. So f of 5 would be equal to what for this function f of x? Should be 3, right? Let's see, f of 100? It's 3. Okay, in fact, this is the graph. If we graphed it, it would be y equals 3, which, if you graph y equals 3, what's it look like? Horizontal line, okay. What's the slope of that horizontal line? 0, everywhere, right? So we should expect to get 0 out of this. We can't force the hand of this thing to make it happen, but we should expect that to happen as we go through the process. Now, in this case, big hint, what is f of x plus h? 3. Doesn't matter what you put in it. We just try to illustrate that. You get 3 out, right? That's what helps you get through this. Now, you do have to be careful. When you get to a certain point, you've got to remember that when you're taking your limit here, is h ever equal to 0? No. Never equal to the target value, right? So it's always either a positive number or a negative number that's not 0. So you'll never have to worry about getting 0 in the denominator when you're trying to simplify these things. But you do need to understand that to finish number 1 off. If you have questions on that, you can always bring them to me. I don't want to give it completely and fully away. That should almost do it for you. Okay, the second one I hope wasn't too bad. What did you come up with? 1. Okay, so here we found, once you did all your work, we found f prime of x is 1. You found here that f prime was 0. Okay, so sort of knowing the answers first here. What did you come up with here, anybody? 3x squared. Huh, okay, so we get x cubed, you get 3x squared. With x squared, remember, we got f prime of x was equal to 2x. What would happen, do you think, if we had f of x equals x to the 4th? And really, I know some of you have already seen this before. Is there anyone who hasn't that wants to give it a try? What do you think might happen? 4x to the third power? Turns out that's right. Okay, what if we had f of x equals x to the fifth? What do you think f prime of x would be? 5 comes down front, x to the 1 less in the exponent. Do you think this works with fractional exponents, like square root of x? X is equal to x to the 1/2 here, right? So what do you think f prime of x should be? Which simplifies to 1 over 2 square root of x, right? Now, what you want to see is this what you come up with when you take the derivative with the limit definition in this one or not? Okay, and you'll see, hopefully you'll get that, okay? Just a little hint. Okay, what if you had f of x equals, I'll just make it a little different than what you've got there, but 1 over x cubed, say. What's that equal to? X to the negative third. So using this thinking of bringing the exponent down front, we get negative 3x to the, and then what are we doing with the exponent? Like we did here, we subtracted 1. Like we did over there, we subtracted 1. So here we get negative 3 minus 1, which is negative 4. Okay, we get negative 3 over x to the fourth. I will always ask you to give your answers with positive exponents. And if it's got a square root, I'd like it to be in square root form versus just a half power. If it's a 1 over 3 or 1 over 5, put it in a radical form. If it's 2/3, I'd begin to not worry about it as much. Okay? But this is information that will be helpful to us. Let's summarize this. This is really, I guess, another sheet, but put it right here. So if we've got the function f of x equals x to the n power. It's called the power rule. What is the derivative of that? Okay, we bring the exponent down. We multiply by x to the n minus 1. We reduce that exponent by 1. This is called the power rule. And here's a more abbreviated form of it. d dx of x to the n is equal to n x to the n minus 1. Okay, again, it's called the power rule. Okay, it's the first derivative rule that we've covered, and it allows us to do some things when we get to section 3.2. So this power rule is really a look ahead to 3.2, but it helps us sort of verify some of the results we get in section 3.1, just helping us see where we're going with this limit process. Okay, we saw a pattern, and that will make it a little easier for us to take derivatives after this. But for now, and whenever I tell you specifically, in section 3.1 for sure, you have to use the limit definition for each of your derivatives. Okay? So work at those. That worksheet, again, is due on Thursday. I will be putting up, I have not yet given it to you, but a web work assignment. And you need to watch the videos for section 2.7 and do the exercises in the book for the formal definition of the limit. So be sure to look at those and do those exercises, the remaining exercises in 2.7. All right, let me know if you have questions. Otherwise, I'll see you guys on Thursday.